Thanks. Thanks everyone for coming, and thanks for inviting me. It's yeah, I'm presenting remotely from um, actually in Canada right now. So it's around 5 a.m. here. So if I seem a little bit tired, that's the explanation for that. Um, but again, thanks so much for inviting me. I'm going to talk about crowdsourcing with video games and mostly about Foldit. Well, a little bit about Foldit at the beginning and at the end, with a little bit of going off in a kind of a different direction to try some things out in the middle. But hopefully it'll all come back together in the end. So yeah, and I guess I'll get started. So yeah, a lot of my work and the work that I've done over the past several years relates to using games for sort of either what's maybe called crowdsourcing or maybe human computation, but basically trying to combine human problem solving and computational power together to solve difficult problems, usually difficult kind of like computational problems that neither humans nor computers would be able to solve alone or would be more difficult for them to solve. And so try to make games that are kind of fun ways to solve problems for people, problems that exist kind of like outside the game. And so this kind of area has existed for a while. These first couple of games are not games that I worked on or that I created, but this kind of goes all the way back to some of the early work of Luis van Aan, who made the ESP game, which was about image labeling. This is kind of shows maybe some of the variety of games that people have made to do these kinds of things. So there have been games for image labeling, games for sort of like OCR, like image to text, kind of like CAPTCHA kinds of things, but trying to make it maybe a little bit more fun. Even games for scientific purposes. So like iWire is all about neuron reconstruction, reconstructing the 3D shapes of neurons, or things like genomic sequence alignment, like Philo does that. And in fact, recently, there's a sort of a game very similar to Philo developed and doing the same kind of thing, genomic sequence alignment, but it's actually in Borderlands. So it's in like a AAA kind of game, but there's sort of a little science area that you can go to and do the same kind of thing basically that you would be doing in Philo, but maybe this can get like more people involved in it. And again, these are not games that I have worked directly on, but kind of to show maybe some of the different applications that games have been used for. And again, this is certainly not all of the applications either. One game that I have worked on for quite some time, in fact, I think it will have been released for almost about 15 years, coming up in a couple months now, is Foldit, which is a game about proteins and biochemistry, and players compete and collaborate to try to fold and design like well-structured proteins. It started when I was at the University of Washington many years ago, and it's sort of a collaboration still between a number of different organizations and universities, including University of Washington. I'm at Northeastern. We also work with Vanderbilt and UMass Dartmouth, and others, lots of collaboration. So a lot of people have worked on this, and even from the beginning. And there have been a lot of players as well to keep playing. We've had many hundreds of thousands of people have come around, found the game and played and so on, and been able to either try the game out or even make some kind of contribution to science by playing the game. So a couple of the accomplishments, just to mention them fairly briefly, are players were able to solve for the crystal structure of a protein, actually kind of determine the structure of the protein that experimentalists have been working on for several years. And actually the players were able to contribute to discovering that particular structure. Players have also been able to fit protein structures into electron density. So this is sort of where you have a little bit of experimental data about kind of where parts of the protein are, and players can actually take the protein and fold it into that. They've been able to discover and develop algorithms for sort of protein structure refinement that we found were actually quite similar to the ones that biochemists themselves were developing. So we actually put kind of some tools for scripting and things like that inside the game where players could write code and kind of maybe codify and automate some parts of their strategies. And it turned out that players were actually quite good at some of the things that they found were fairly effective at refining protein structures. Players were actually able to redesign an enzyme to be more sort of effective than the initial enzyme structure that we gave them. And in fact, somewhat more recently than these, players are actually able to design some protein structures completely from scratch. So basically starting from kind of a blank template kind of protein structure, they were able to basically design protein structures in the game that when they're tested sort of in the lab, they sort of experimentally folded up into the same structure that the players designed in the game. And so this is a game for sort of crowdsourcing. So we wanted people to be able to come and play the game without necessarily having a lot of background in biochemistry. And we found that is, for a large part the case, that people who come play the game don't necessarily have much of a formal background in biochemistry, maybe took some in college or something like that. So in order to make the game, accessible, approachable to players who might not know the sort of the background material, the content, the game is introduced by a series of tutorial puzzles that start off with things kind of like this. They're relatively sort of small, simple structures that have very specific things wrong with them that they're supposed to fix. They have a goal score where we know, what we want them to fix, and then when they fix it, they sort of get reward, the confetti and sounds and animations and that kind of thing. And the puzzles, these tutorial puzzles, right, they get harder and harder, and they have more and more things wrong with them. Then they get harder to fix, and they introduce new tools and that kind of thing for the players to learn about, to the point where they get to the scientific puzzles, which are kind of more like these, which have more things wrong with them. We don't have like a particular goal score, and often in many cases, we don't actually know. We don't know the answer, right? I mean, in these scientific puzzles, oftentimes we don't know the answer, and we're sort of like going to the players to see if they can find a good structure for this protein or a good design. And so you can see here there's no target score. In fact, it's kind of hidden right now up here, but these puzzles are organized as a leaderboard competition where you can see your score here in the top that updates as you're playing, but you can also see the score of everybody else who's particularly currently working on this puzzle, and you can see your score and how it relates to their score. And so it's a leaderboard, people trying to get first place. So as long as you're not in first place, there's sort of a higher goal to reach. And I guess if you're in first place, you can try and expand the gap between you and second place and so on, and have a better lead and that kind of thing. So there's a leaderboard competition. It's organized this way again because we don't necessarily know the best score or the best answer for the particular protein structure that we're looking at right now. There's also groups. Again, it's sort of hidden up here right now, but the players can organize themselves into groups and sort of share structures and improve on each other's structures and that kind of thing. And so one of the things that we've also seen is that players working together seem to be able to come up with, kind of more interesting results or interesting structures or answers than just individual players working by themselves. So it's organized in this way. So there's a bit of competition and there's a bit of collaboration as well. And actually, the whole Foldit game is built on top of this piece of biochemistry software called Rosetta that handles all of the biochemistry computations and things like that to make sure. So it handles sort of like figuring out what the score is. So the score is like a reasonably scientific accurate representation of the current structure of the protein that the player is creating, and that updates as they play. It's the same. I don't know, maybe if you're familiar with, or you could look up like Rosetta at Home. It's a screensaver that does a similar kind of thing, but it's not interactive, but it's also using this Rosetta software underneath for the scientific calculations and optimizations and scoring and that kind of thing. So, so that's within Foldit, right? Particularly in these tutorial levels, there's a whole bunch of levels, for example, that are meant to teach particular things, but in the sort of the standard Foldit, everyone gets the same levels in the same order for the tutorials. And even in the scientific puzzles, they run kind of weekly. The puzzle will be up for kind of a week, and everybody works on the same scientific puzzles during that week, and then they can collaborate and see the leaderboards and that kind of thing. And everybody gets the same tutorials in the same order and kind of the standard Foldit. But one of the things that it might help out is something that can maybe adjust itself to a particular player, right? When they come in, if they if they do have more of a background in biochemistry, or maybe they have more of a background in playing spatial kinds of games like Tetris and things like that, they might be able to progress through things faster. For example, they might be able to work on kind of more challenging scientific puzzles and so on than players, who maybe have less background in biochemistry or less experience playing games and things like that. And so this kind of tutorial and scientific organization we have now with the levels where everybody works on the same thing or gets the same things kind of in the same order, maybe we can do something a little bit different, a little bit more tailored to each individual player, right? And so that was one of the questions kind of that we had asked. If you have sort of, as we do, a bunch of kind of levels and scientific puzzles and things that we want players to work on, some of which, in this case, are meant for training, and some of which we're interested in the answer for, what sort of task or level would you want to assign to or give to a particular player to play next, right? Can we, come up with a sequence of things to do, of levels to play that kind of adjust to how well an individual player does? And so that was a question that I was curious about as well. Kind of like dynamic difficulty adjustment in games, right? Not too uncommon to use, I think. So the inspiration that for this part of the project that I'm talking about that we took was based on player rating systems. And so these are kind of the systems that several different games use to kind of give players a rating that kind of represents how good they are at their game. And this is, there's different systems from different games. Probably some of the more better known ones are ELO, which is oftentimes used for chess. So if you've ever heard about like a grandmaster's rating in chess or something like that, and some number like 2,500 or something, that's probably their ELO rating. And then there's other ones like True Skill, for example, that are more used for like matchmaking and maybe even team matchmaking and things like that. But the basic idea of these is, players will get kind of a rating based on some estimate of how good they are in the game, and that can be used for matchmaking, for example, or for estimating kind of like the outcomes of games and things like that, where you don't know the results, right? So this seems very applicable to these kind of crowdsourcing games where we have players who are coming in and we don't necessarily know their level of skill or background, right? And then we also have a lot of puzzles, maybe that some of them maybe we've designed to particularly teach some particular thing, or maybe there's some kind of scientific puzzle where we don't know the answer. We don't know, we don't necessarily know how difficult they are. Maybe we have a guess of where we think they would go, but we're not totally sure, for example. And so the kind of basic approach that we took was to use an existing player rating system and treat the levels as though they were players, basically. So instead of just giving players ratings, we give the players ratings, and the levels also get ratings. And then we treat the player attempts at the levels as though they are matches, in like a chess match, for example, right? A player attempting a level is kind of like two players playing against each other in a chess match or something like that, or another player versus player game. However, in this case, one of the players is just the level, right? It's not an actual player. And then we can use the results of these for trying to estimate the ratings of the players, the ratings of the levels, and then we can use this for matchmaking kind of in the same way that matchmaking could be done in, say, chess or some other PvP game, and see how that works out. So again, kind of the two kind of main properties that we're interested in a player rating system is that if you have a player and a level, and they have, their ratings, basically, you can use that to estimate the likelihood of the player winning, right? So roughly speaking, if they have the same rating, it's probably a 50-50 chance. If the player's rating, and the higher the player's rating gets above the level's rating, the more likely the player is to win, and vice versa. The player has a lower rating than the level, the player is more likely to lose. So we can estimate the likely sort of win-loss of a particular matchup between a player and a level before they actually even attempt the level. And then the other aspect that is useful is, or sort of relevant here, is that after the player plays the level, we can then update the ratings based on that. And so again, roughly speaking, if the player wins, their rating will go up and the level's rating will go down. And if the player loses, the player's rating will go down and the level's rating will go up. And sort of roughly speaking, this is kind of done proportionally to how kind of surprising, maybe you might say, or unlikely the outcome is. If you have a really good level that beats an easy level, if you have a really good player, if you really expect the player to win and then they win, you probably won't adjust the ratings too much, right? But if you really expect the player to lose and then they happen to win, then the ratings would get adjusted sort of more than that. So we can, before a player attempts a level, we can sort of guess how likely they are to win. And afterwards, we can adjust ratings based on what we actually saw happen. And so I'm going to talk a little bit about, this is where I kind of go a little bit on a side path before coming back to Foldit on another project, although this was a whole other very interesting project in and of itself. But we were looking at kind of a little bit of a similar game, another sort of crowdsourcing human computation game, but we could use it to test out some of the possibilities and some of the ideas and see how well they worked. And then in the end, we'll sort of be able to bring them back into Foldit and see what happens there. So I'm going to talk a little bit about this other game called Paradox and what we did there, looking at task ordering using these player rating systems. So Paradox kind of is similar to Foldit in some ways. That players are trying to solve a puzzle. It's a constraint satisfaction puzzle, and they have a target score. You can see, similar to Foldit, that they're trying to reach here, and you kind of change the colors in this to try to get them to line up with what they're supposed to be, and you can just kind of change them with this brush. And this is a relatively simple level. They get more complicated than this, and there's different tools you can use to change the colors and try to optimize things and so on. But it's again, it's kind of a puzzle game. You're trying to get it to reach a target score, not unlike Foldit. And then you can also kind of forfeit the level too as well if you feel like you've gotten stuck. But it's kind of like Foldit, but a little simpler. So to look into this with Paradox, in fact, there's kind of this is what I'm showing here is kind of a newer version. This game, and this is also the same game, but kind of a different visualization style that we used for it. But it's also Paradox, the same game essentially. We did sort of a two-phase experiment in this. So we had the Paradox of the game. We recruited players to play the game from Mechanical Turk, and then we used the player rating system called Glyco2, which is another player rating system that is similar in many ways to ELO and things like TrueSkill. In some earlier experiments, we had done some analysis, and it seemed to work pretty well for our particular use case. I would say I would sort of roughly describe it as kind of in between maybe Elo and True Skill, just in terms of kind of complexity of how it works. And so we found it was a nice, maybe in-between point that worked pretty well for our particular use case. So in the first phase of this sort of study experiment, we got some data for the level ratings. So we have a bunch of kind of, right, as I was describing before, we have a bunch of players where we don't necessarily know how good the players are. And then we have some levels here, which I'm representing as these kind of little, circles here. We don't know, the ratings of them. And so we had the players come in and play, and they were basically given the levels in just random, completely random order. In this case, we weren't trying to do any matchmaking. We're just trying to get some information about how well players play. And so after we had done that, we then just sort of played back the results of those into the rating system. So we kind of simulated the gameplay back into the rating system. And in doing that, we did this, right, this where if we know the ratings beforehand, and then based on whether the player wins or loses, we can update the ratings afterwards of the player and the level. Although in this case, we just kept the ratings of the levels. And so at the end of this sort of phase one part of things, we had ratings for all the levels that we wanted to use in the system. Then in the second phase, so that was sort of just kind of the data gathering for getting the ratings for the levels. In the second phase, we actually wanted to see if doing some kind of matchmaking with this information or using this information in some way would actually make a difference at all in how people played. So we did this sort of experiment where we gave players randomly some different strategy kind of, or a different approach for ordering the levels that they got. So some players, in this next phase, when players came in, they would either get the levels in just basically increasing order, essentially. So they would start at the lowest rated level, and then they would get the next lowest rated level and the next lowest rated level, and so on. So this was not actually like adaptive to the players at all or adjusting to them. But it did use sort of the rating information from the first phase, right? So everybody who got the sort of increasing order just went from the easiest level that we thought up to the hardest, essentially. And they all got the same order. Some people would also get the levels in completely random order, so completely ignoring the ratings entirely, and just kind of the same as the first phase, just get a completely random ordering of levels. And some players got this, what we called in this version of the experiment, matchmaking order. And so this curve kind of shows, what it shows is the function that we used from the player's rating to how likely we wanted them to be to win the next level that they got. So roughly speaking, right, you can see, they start at 1500. When a new player comes in, their default rating is 1500. So we want to try to start them off with a level that they have, roughly a 90% chance of winning. And then, right, if the player wins, their rating will go up, and then we'll actually drop the sort of likelihood that we want them to win the next level. And if they lose, right, then the likelihood that we want them to win the next level is going to go up, right? So as they get better, they should be getting sort of harder and harder levels for them. Not only is their rating going up, so that kind of adjusts the whole estimation of the likelihood, but we're also decreasing the likelihood that they might win the next level to make it harder. And this, right, this kind of makes sense for games. Like, we kind of expect the games to get harder as we go on. But this will sort of adjust based on if they win or lose, that difficulty of the next level will go up or down. And to find that, right, we have this pool of levels with ratings, so we can just kind of search through that and find a level with that we think is closest, has sort of like the likelihood of the player winning that is closest to the one that we think we want the player to have. So when we did that, we got some information, right, about how players played and how well they did. And we can see that we can look at a couple just more example trajectories of the sequences kind of levels that players got as they went through the game. So for someone who, this is a player who went through the increasing sort of ordering, you can see they start at the easiest level here, so with a pretty low rating. So each dot is a level, and then the y-axis here is the rating of the level, or at least with the dots, it's the rating of the level. So green means they were able to beat the level, orange means they skipped it, and red means they forfeit, they kind of gave up, which we count as a loss for the purposes of a matchmaking. So you can see in increasing order, basically this player got, pretty much according to the rating systems, low difficulty levels all the way through, and they beat most at the beginning, and then they kind of skipped a bunch, and then they left. And in fact, everyone in the increasing order should get levels kind of basically the same ordering of levels, although whether they win or skip or forfeit is a different thing. And so if we look at a random ordering, right, this is a random ordering of the levels. The ratings of the levels is kind of all over the place. But you might get a very hard level right at the beginning here, right? A player got a very difficult level right at the beginning and they weren't able to beat it. But you can see at some points, right, they were able to get actually quite difficult levels and were able to complete those levels even before they gave up. But you can see there's no real structure, I guess, other than the randomness to the levels that they got. And then this is the matchmaking order, one player's sort of trajectory through the matchmaking order. Now we've got the dots, which is the level ratings, but the line is also the player's rating. And it just naturally sort of happens, right, that they start off with a particular level, and as they win, as the player wins, right, their rating, the line for their rating goes up. And then when they lose, that it goes down and they get an easier level. So you can see just using this sort of matchmaking system, the player's difficulty goes up, or the difficulty goes up as the player wins, and then it comes down when they lose, and so on. In fact, you can see based on sort of that curve, right, the ratings of the levels kind of sort of catch up with the player's rating and kind of almost like overtake it, right, at a certain point. And this is kind of this dynamic adaptation. And so I guess one other thing maybe I can mention is, oftentimes if you're doing player versus player matchmaking, for example, you might want just to have a sort of a 50% kind of win rate all the time, right? So that it's a well-balanced match where either player is sort of equally likely to win. However, in this case, since we're, playing against levels, we don't really have to worry about the levels sort of whether the level wins or not, right? We can just sort of take things from the player's perspective. And so, of course, we get some data on how well players do in the game, and hopefully there's not too much going on in these graphs, but roughly speaking, the summary is down here, is that players attempted more levels and completed more levels, right? So it's increasing order, matchmaking order, and random order. Players attempted more levels and completed more levels kind of on average with just the increasing order and the matchmaking order. So when that kind of makes sense perhaps when they were given random the random ordering, they weren't able to sort of complete as many levels. And interestingly, we didn't really see any kind of difference in the time spent across the three different ones. Players spent about the same amount of time. And again, so in this case, it was just 6 minutes, so not necessarily like a super long amount of time. And then more difficult levels were completed with matchmaking order and random order. So with the this also kind of maybe makes sense because with the increasing order, players, they spent most of their time just on the very easiest levels that we found. And with random order, right, there was some chance, right, players would get randomly get a very difficult level that they were able to solve using the tools in Paradox, right? Again, this is all for Paradox. So in terms of kind of what we saw with player performance, we didn't actually see really any difference in the time spent across the different versions. So perhaps they were all kind of equivalently interesting to the players. But roughly speaking, it seemed like players were able to do more or complete more things with the matchmaking order and the increasing order. And players were able to complete kind of more difficult things with the matchmaking order and the random order. So in both cases, the matchmaking order seemed to compare favorably to the other orderings that we looked at, which I think is good because, right, we want the games to be kind of fun for the players. We want them to be effective ways for players to actually solve the kinds of problems that are in the games. In this case, for paradoxes, sort of constraint satisfaction problems that we can put into the game. Since roughly speaking, the amount of time the player spent, we didn't see sort of a difference there. It seemed like perhaps this adaptive kind of matchmaking was spending players' time more efficiently, right? Sort of for the same amount of time of playing the game, they were able to kind of do a little bit better in terms of the task. And in fact, even just the increasing order, right, also had seem to have some kind of benefits, for example, compared to random ordering in some cases, right? And so even though that wasn't actually adaptive, right, it wasn't adjusting to individual players, it did incorporate sort of the ratings from how well players did in the first phase. And so even that could potentially be useful for ordering levels. And I'll come back to this maybe a little bit later, but this might be a good kind of generic approach to doing player level matchmaking, right? Because again, in terms of what the game needs to kind of support, you just kind of need to know, roughly speaking, right, if a player won or lost a level to use it in this way. And so we've actually tried to apply it to some other games as well, since it's fairly flexible and doesn't necessarily make a huge number of assumptions about what's going on in a particular game. So and again, that's just probably more of a consequence of using these already fairly flexible kind of rating and matchmaking systems that existed previously, right? And so we can adapt them to this situation, and perhaps they could adapt to other situations as well. For example, Foldit. So now we had seen that the matchmaking, it had some impact, right, in these other games, and we're sort of curious if it might transfer over to Foldit and work in Foldit as well. And so to do this, we added a mode to Foldit, which was called the Dojo. So this was kind of a new kind of area or a separate area within Foldit that was separate from the standard tutorials and the scientific puzzles, but it was specifically this area where you could kind of go to get this adaptive training kind of experience, right, that would try to adjust based on how well you were doing on the previous levels. And so because in Foldit there was not actually any way to lose a puzzle such as it was before this, other than kind of giving up, we wanted to make it a little bit more challenging than that. So we added this kind of concept of stamina for the dojo, where when you make moves or as time passes, the stamina kind of decays, and if you run out, right, then you lose the puzzle. So there's actually some sort of actual criteria in the dojo mode for actually kind of like losing a puzzle other than just giving up. So beating the target score is a win for the level, and if you run out of stamina, you lose the level, right? And so this was put into the kind of the live game, right? Foldit is out, Foldit is live, and this mode was sort of put in as a way something you could do from the menu, and players could try it out. New players could come in and try it out, and so on. And so for the purposes of Foldit's Dojo, we did another sort of data gathering phase or round where we put in about 71 levels or so. In fact, we initially set the ratings kind of heuristically. One of the team members did that since they were going out into this game that people are already playing. And then we updated the ratings from the actual data. And so this is kind of just a plot of the distribution of the ratings. So you can see they have a pretty good coverage of kind of the space of ratings that levels could have, from quite easy to quite difficult all the way up here. And similar to before, we also, when players would come into the dojo to play in Foldit, we would some of the players would sort of get assigned to different orderings of levels. And similar to before, we had linear, which was where you just went in strictly, from the very easiest one up to the hardest one. Random. In this case, what we're calling logistic, which was a similar kind of difficulty curve as I talked about before, although not completely identical. And fixed, which was looking at just everybody gets the same, regardless of your particular player rating, we try to find a 70% win rate. So the game doesn't, you're getting better. So what the system thinks you have a 70% chance of winning maybe changes, but we always try and just give you the same win rate. So these two, logistic and fixed, are using sort of the same kind of matchmaking system as before, although they're using different sort of difficulty curves in the game, right? Logistic is probably going to get harder, faster, whereas fixed is probably going to be easier. And so we were sort of curious if that made a difference, right? And 221 players ended up in this. And so again, hopefully the charts are not too busy, but the kind of summary is that when we looked at these 4 different versions, we found that the logistic curve, players spent a little bit longer, kind of on average, right, than random. In terms of time played, we found that in terms of the levels that players completed, there were random was kind of lower on average, perhaps than all of the others, right? Not too different, I think, from what we saw before. And logistic was a little bit higher than fixed. So random kind of lower than the others, and logistic compared favorably to sort of fixed, which was the easy, so the 70% chance of winning all the way through. And also, just to note, these are relatively low numbers here. It's like, I think like 2s and 3s and 1s, for example, right? So it's not like a very high number of levels in general, on average, I guess I should say. However, there were players who completed, very many levels. In terms of the highest difficulty of the level completed, again, random was lower, sort of on average, than the others, although the others, we didn't really see a difference between them. And we looked at like the highest rating that a player achieved. We didn't necessarily see a difference between those. So just in summary, kind of in the Foldit Dojo version of this experiment, we saw that the complete random ordering was generally worse than the others, pretty much in any comparison where it came out different, right? Which was a little bit different than we saw, I think, in Paradox, right? This maybe is because the hard Foldit levels are quite difficult, right? And they might actually be harder than, the hardest kind of Paradox levels. Like I think in Paradox, there's some chance of getting like a hard level and being able to use the tools in the game maybe to solve it. Whereas in Foldit, it might be much more difficult to solve a hard level that you're given. And so this might be the difference here. And the other 3 orderings, logistic, fixed, linear, they were quite similar in most cases, although logistic sometimes seemed to improve compared to one of the other ones in terms of the time spent and the average completed levels, for example. So in this case, it does seem like, logistic is the one, this dynamic matchmaking curve with this difficulty curve where things kind of get harder faster as you get better, seem to be comparing favorably to some of the others in some cases. Although again, the linear, right? Linear was just still a kind of the same ordering for everyone. It wasn't sort of necessarily adaptive, but it did use this rating information from before. So we were able to, based on what we kind of learned in some of the work with Paradox and some of the earlier matchmaking work, was able to use rating and matchmaking in what we were calling like a live game, right? This game that already exists, that already has people coming in and playing it. We did it by making, in this case, kind of this separate area where players could come in specifically to get this kind of adaptive experience. Right, it was this kind of a separate area which didn't affect kind of the standard tutorial and the scientific puzzles and so on. But it might be interesting to try to integrate it more fully throughout the game, right? But it was a separate area where players would only get this if they came specifically to this particular area in the game. As I was saying, there's more work to do in this. For example, integrating into things like science puzzles and the scientific kind of content of the game. For now, it was mostly for sort of like training and practice. And in fact, I think this general approach might be useful in other games, other sort of crowdsourcing, human computation games, right? Games where we don't necessarily know the answer, right, to the puzzle or the content that the player's looking at. And so I think beyond just these sort of crowdsourcing games, right, where we don't necessarily know the answer to the level beforehand, there's other areas like procedurally generated content or player generated content where there's content going into the game, levels, things like that, that wasn't designed beforehand to have a particular difficulty, right? And so it might be a way to estimate those kinds of things. And in fact, even in Foldit, in the Foldit sort of version of this, we actually initially set the ratings of the levels kind of heuristically based on what one of the team members, how difficult they thought they were, and then those got adjusted by this. So even if beforehand we have some kind of estimation of how difficult we think things might be, this sort of rating system approach can actually adjust them. And again, it seems fairly flexible, again, largely because of the flexibility of the rating systems themselves. So it possibly could be used in a variety of games as well. In fact, we've done a little bit of work beyond that, what I talked about here in the rating systems, mostly in Paradox, but looking at things like not just predicting whether a player will win or lose, but trying to estimate, for example, what score they'll get on an upcoming level, and more looking at kind of like the impact of the difficulty curve, right? That function from player rating to likelihood of them winning the next level, and kind of what impact that has, and how you can, if you adjust it, you can sort of trade off these kinds of things like how many levels players sort of attempt and complete, and how difficult they are, and that kind of thing, by just kind of like adjusting this curve and seeing what impact that has. So in this talk, I was sort of talking about Foldit sort of at the beginning and some of the motivation for that. I talked a little bit about another direction that we went in, looking at Paradox and the matchmaking and dynamic difficulty adjustment here, and then basically bringing that back to Foldit and how we connected those together and actually brought the dynamic matchmaking into Foldit's Dojo mode. And so I've worked on a number of sort of games for crowdsourcing citizen science. Of course, I mentioned Foldit, it's about protein folding and protein design. Paradox, constraint satisfaction. I've worked on several other games, including some looking at things like motion classification. I've done some augmented reality work, augmented reality game for image categorization and classification. I've worked on some games for software verification, object categorization, using trying to make more like platform kind of games, but that also have human computation aspect of them, since oftentimes the kinds of games I'm working on are more like puzzle-y kind of games. And also, currently kind of in a very early development, but a game for like container stowage and loading containers on ships efficiently and that kind of thing. So thank you very much. Again, thanks for inviting me. Thanks for listening. Hopefully, there's something useful and interesting in there for you. And again, a lot of this work that I talked about was done in collaboration with, and oftentimes by, students, right, in collaboration with other students and faculty and people. So I want to especially thank, the collaborators on this work, the people who supported it and funded it, and definitely the people who came in and played the games, because sure, without people coming in to play them, none of this would have been possible to find out and learn about. So thanks.
So I wanted to ask one thing, which is the player base, the community size of Foldit currently. How many people are there playing the game at this moment?
That's a good question. I'm not sure for right at this exact moment, but I know over the years there've been, we say there've been many hundreds of thousands of people who have played. I would say the core, again, this is probably my kind of estimate, so I can't say how accurate it is, but there's sort of a core of maybe several dozen, I would say, players, and then there are new players coming in. So in any particular week, there might be dozens, maybe to hundreds of players playing the game, but there's definitely sort of a core community that is not super large, but they've been playing the game for a long time, and I think they're very involved and engaged in the community. Yeah.
Yeah. So the reason why I'm asking is that the kind of the super fantastic and detailed talk about the matchmaking, that is the motivation behind there. Is it about retaining the players, or just ensuring the more enjoyable kind of a journey of playing several levels? Like, what is the main motivation of thinking these kind of things in crowdsourcing games?
Yeah, that's an interesting question. I mean, I think both of them would be nice. I'm not sure that the sort of the matchmaking dynamic difficulty adjustment, it would be nice if it helped to kind of grow the community. I mean, it puts sort of more content, I think, in the game, that different modes that players can try out, and things like that. I think maybe, I think there's definitely so a little bit of both. I think there's a kind of a long ramp, I think, from coming into the game and not having any experience to the scientific puzzles. And I think this is probably true in a number of these sort of citizen science games that build up to more complicated problems. For example, maybe like iWire, right? iWire has a similar community. It's been around for a long time. So it would be nice if we could kind of smooth that onboarding ramp and help more players get to the point where they're more involved in the community. On the other side, there's also been, I think, some work looking at, I think, what sometimes has been called like dabblers in kind of citizen science kind of games. People who are and this is probably even more a larger majority of people who kind of interested, come check it out for a little bit. And I think if there's more of a way to sort of apply that dabbling kind of more effectively too, I think that would also be useful. So I think a little bit of, ideally a little bit of both,
right,
if possible. But it's challenging, and I think you saw in the data that the times and the number of levels completed, kind of on average, are fairly low.
Yeah. So what do you think? I think this question is inspired by a pre-assignment from a student, that how do you make a science game entertaining? Like, Foldit is sometimes maybe not so gamey, but it is a puzzle. So how do you, does it have to be entertaining in itself to be successful as a citizen science game? I mean, does there have to be, for instance, a storyline or something like that, or is it just in itself, because it is science project, that it motivates people to participate? That's what I'm aiming for.
Yeah, my sense is probably the science part is a large, if not most, of the motivation. For example, there's certainly a number of citizen science projects that aren't games, right? I mean, most of them are not games, and it's the motivation there is the science and contributing to the science. But I think hopefully we try with the game aspects, I think, to make it maybe a little bit more interesting, engaging, and that kind of approach. So, in a way, right? Sometimes I think some of these kind of like design principles or ideas from gaming maybe applied to citizen science, right? We're working to try to make the tutorials and the onboarding more interesting and adaptive to people, try to give people sort of like ideally clear, feedback about what they're doing. Again, this sort of like difficulty kind of maybe flow kind of ramp from starting the game to contributing to the science. I think, and it may be more applicable to these kinds of citizen science tasks that are difficult and take a long time to get into, perhaps, and a long time to reach the scientific aspect of things. Definitely not that Foldit has done it perfectly, and right. So we're always working on that and trying to improve things. And a lot of my, other, like the work with Paradox was basically trying to look at, can we do these kinds of things in a general way that might work across games. So something that we learned from one game, maybe we can apply to other games, like I was talking about here. So yeah, hopefully that somewhat answers the question.
Yeah, I think we're running out of time. I have a lot of other questions. It's super fascinating to see such a kind of a long journey of a game to still giving out to other citizen science game projects, an example of what we can achieve with games. But yeah, thank you, Seth, for your fantastic insight, for the current developments inside Foldit, and hopefully see you in somewhere in game conferences, perhaps. Okay.
Great.
Bye.
Thank you very much. Bye.